those of you who don't know me, my name is Joe Winston and I'm the nTopology account manager here at Measurement Solutions Limited. Today we're going to go through this webinar to show you the lightweighting capabilities within nTopology. And I'm going to show you it in the context of some end-of-arm tooling that we've created for one of our scanners. So we can see the original picture of the scanner on the left, the optimized version on the right here. So I'm going to go through some slides to give you a background of firstly MSL and nTopology, and give you a little background of how the software works. Then we're going to jump into the software itself, and I'm going to show you the workflow that went into creating this lightweighted and optimized clamp. So first, a quick background on MSL. We've been a reseller of predominantly metrology equipment for the last 24 years. And career-form scanners are really the bulk of our business now. So on the right here, we can see one of our career-form handy scans. This is a handheld 3D scanner. We also have the option to bolt this to an automated system where it's on the end of a robotic arm. And that's the application that we're going to be looking at in the webinar today. nTopology, the company was founded in 2015. And some of you may know it from its first software platform called Element. So Element was predominantly focused on lattice generation and lattice manipulation. And it was aimed to fill a void where traditional CAD packages really fell short in dealing with these quite complex structures. nTopology had a very unique mathematical architecture that made it really good at manipulating and creating these complex structures. And nTopology soon realized that this math-based approach had advantages far beyond just working with lattices. It gave the ability to design parts, a completely new and unique way of designing parts based on maths and data. So in 2018, nTopology took all its learning from Element and released their next software package called Platform, which is the package that we know of today. Lockheed Martin were one of the first companies to see the potential of Platform. We're the first company to invest heavily in the software. 2019 and 2020 saw a series of more investments, and the list of companies using the software has grown and grown over the last few years. nTopology has quite a few unique features that really differentiate it from traditional CAD packages. These are just kind of the key three features that I'm going to focus on now, and you're going to see a bit more of in the software as we go through it in a little while. So implicit modeling, all of nTopology models are implicit models, and implicit models are based on mathematical functions. It makes the models very lightweight, easy to work with, and easy to store, and geometries are unbreakable. So we can see this little screen recording of a gyroid structure being updated within this engine block. You can see just how quickly the parameters can be adjusted and how quickly the geometry can update. Field-driven design creates the ability to quickly process complex features and operations, and simulation data can be converted into fields, which can drive generative design. So within a field, this is the idea that every point in space is represented as a distance. By using maths, we can assign a positive or negative number to that point. Any point that's given a negative number is represented as a solid, and anything that's given a positive number is represented as free space. That's how nTopology represents models in the software. So we can think of this as a helium balloon. So if we blew up a helium balloon in a room, all of the helium within the balloon would be in nTopology represented as a negative number or a solid. The skin of the balloon would be the boundary of the model, and the free air inside the room would be free space within nTopology. And it doesn't really matter whether we're making a simple shape, like the shape of a balloon, or a complex gyroid structure. Everything works the same. The reusable workflows. So in nTopology, we create a process rather than a description of a 3D model. and it leads to repeatable and reusable customization. So because implicit modeling and field-driven design creates such robust models that are unbreakable, it means that we can reuse workflows. So in a traditional CAD package, we might update a property, a radius at the top of a design tree, and further down the design tree, we would have errors and the model would break. In nTopology, we don't have those issues, and it gives us the ability to create reusable workflows. So in the example down here, we can see some patient-specific CAD data. And within nTopology, we can apply a stochastic lattice to each of these models. So the challenge for today's webinar, we had to take our original RoboSCAN-R clamps, which we can see here. These are the clamps, this is the scanner, and this is where it's attached to the robotic arm. So to take these clamps and make them lighter, cheaper, and improve the performance. And that's potentially quite a paradoxical challenge within engineering. We would typically expect cheap and light parts to perform poorly, and we would expect a part, if we were making it lighter and improving performance, to be more expensive. But the challenge was set here to make the parts lighter, cheaper, and to improve the performance. Our only real constraints were that the interfaces with the arm and the interfaces with the scanner had to remain the same. And ideally, we were looking for more ventilation for the scanner as well. So the scanner, as you can imagine, there's quite a lot of electronics that go on inside here, and clamped between two solid blocks of nylon, there was the potential for the scanner to overheat and degrade performance. The last part of the challenge was really to show off what nTopology can do and have them ready for Mac 2022 earlier this year. I think it gave us around 12 working days to come up with the CAD model, get it printed, and have them ready on display at Mac. So the solution, I'll run this little video showing the optimized clamps in action at the Mac show. So the solution is to run the components through a topology optimization. So the topology optimization reduced material, therefore reduce the weight of the part and increase the efficiency of the end of tooling. We also turned the areas that hold the scanner into a lattice structure. So this gave us further material reduction and increased the ventilation, so improving the performance of the scanner. Essentially what we did was take advantage of the fact that in AM, added complexity is often free, and in this case, it was actually a lot cheaper. We can see a little summary box here of the weight, cost, and material usage of the original version, the topology optimized version, and the savings that we were able to achieve from the part. Here's a couple of pictures, picture of the original block here and of the optimized block. You can see the optimized block is infinitely more complex, but with the wonders of AM, this more complicated block, because it was half the material, it actually worked out cheaper. So unless anyone's got any questions, we will jump into the demo. If you do have any questions, there's a little Q&A tab on the left-hand side of the screen. Just drop your question there and I will get to it. So without any questions at the moment, let's jump into the software itself. So here are the original clamps, the left-hand side clamp here, the right-hand side clamp. These are just brought into nTopology as step files. And all I've done so far is just split out a few faces. So I've got our mounting faces here and here, and I've split out our interfaces. So the faces that connect with the faces that are interfacing between the two parts. So I'm going to focus to start with on just this left-hand side clamp. So I'm going to create all of our workflow in the context of this left-hand side clamp. And then with the wonders of nTopology's workflows, I'm going to package all of this workflow into one little custom block. I'm going to reuse that to do the right-hand side. So to start with, in our notebook, I'm just going to add a few sections just to keep the I'll keep the notebook nice and organized. Our first section is going to be our left-hand side topology optimization. We need a left-hand side lattice side final part, which is basically just going to be a merge of the optimized part and the lattice. We're also going to add a section here for variables. You'll see why we're creating that a little bit later on. Okay, so there are a few extra faces that I'm going to want to keep here. So we've split out mounting faces, split out the interfaces. I'm also going to make sure that I keep these bolt holes. The bolt holes are going to be quite an important feature of the topology optimized part. So all I'm going to do is hold down Control and click all of these faces, just to make sure that we can reuse them a little bit further down the line. One more set of faces, select here. And then I'm going to right click, create a CAD face variable list. And I've got a list of faces here. I'm going to call holes. The next thing I'm going to do is I'm going to import a couple more step files into this workflow. I'm going to use these to give us some guidance on where our force faces are going to be. So it'll just take a few seconds to import these step files into nTopology. There's the first one, the second one not far behind. So we can see that when this assembly is set up on the robot, you can imagine the robotic arm would be here and the scanner sits here. So the force faces are going to be kind of the interfaces between this bracket here and the clamps. So these faces here. First, make sure I've just got the clamp selected. These faces here, and on the other side, these faces here are going to be the faces for our vertical force. These faces. And when the clamp's rotated around 90 degrees, we've also got some mounting points for those brackets here. It's spun around at 90 degrees. Our force faces be here, here. I'm going to right click, and I'm going to call these force faces. Okay, so I shouldn't need these brackets anymore. Let's remove these from the workflow for now. We can just bring them back in later if we do need them. But for now, I think we've got all of the faces that we need. So we can start with our topology optimization. I'm going to drag in our topology optimization block. Topology optimization. Here we have all of the parameters that go into building a topology optimization. I'm going to split a few of these out as variables just to make the workflow a bit easier to follow. We've got some parameters that are already set in here. So maximum iterations of the optimization, the boundary penalty, so whether we want material specifically on the outside of the space envelope or not. For now, the first thing we're going to do is create our model for the FEA. At the moment, this is just a CAD model. It's imported as a step file. But if I double click, right click, and say convert CAD body to implicit body, we can really quickly turn it into an implicit body. I'm going to rename this our design space. Now I'm going to turn it into a mesh. So I'm going to need a block that's called mesh from implicit body. Make this body a variable. I'm going to call this body to mesh. This is the first block that I'm going to drop into our variables section. I'm going to apply a tolerance of 1 millimeter, nice low tolerance, to make sure that we pick up all of the features that we need to. Now all I have to do is drag and drop the design space into this body to mesh block. It's going to convert that to a mesh. Now here we've built up almost the start of a mini workflow. So it doesn't matter what I put in that first block, whether I use our design space or whether I use this cube, it's going to feed into this mesh for implicit body block and turn whatever model I put into here into a mesh. So we don't want to use the cube, we want to use our design space. So here it's picked up the fidelity of the model quite well. There are a few flat faces here where we've got lots and lots of triangles where we don't necessarily need them. We want kind of a high density of triangles in these more intricate areas. But in these flat faces, we don't need that at all. So I'm going to remesh my surface. And here we have loads and loads of control over the mesh. So I'm going to set my edge length. I'm going to drag my edge length out as a variable because I'm going to use that again further down the line. I'm going to make my edge length 5 millimeters, shape a triangle, and we've got loads of control over the rest of the mesh here. One interesting parameter that we are going to change is the growth rate. So the growth rate is the rate at which the size of adjacent elements can grow. So at the moment it's set to 2, meaning that the adjacent triangles can double in size. So we can see how quickly we go from a fine mesh around this edge to a much bigger mesh over here. So a high growth rate is good if we're trying to reduce the triangle count within a mesh, but in this case we want to really keep these intricate faces very detailed. So rather than a growth rate of 2, I change it to 1.5, which means that rather than the adjacent elements doubling in size, they can only grow by 50%. So this is going to give much more accurate mesh in those detailed areas we want to keep. So in just a few seconds, we're going to have a much higher resolution mesh in these detailed areas. And you can see it just takes a little longer for the fine mesh to turn into a bigger mesh. Okay, so now we have a surface mesh, but the volume of the part still hasn't been meshed. So the next block I'm going to need is a volume mesh. I use my surface mesh at the top here, and for my edge length, I will keep this the same as what we used previously. I'll keep the edge length and the growth rate the same for our volume mesh. Now we're going to see a mesh that is converted into a mesh on the outside and also a mesh on the inside. The last thing we're going to need to do is turn this mesh into an FE volume mesh so that it's ready for our topology optimization. Okay, so I'm going to make this a variable and call it FE volume mesh. The model for the topology optimization, we are going to need a mesh, which we've just created, and we're going to need to assign a material. So there are a list of pre-populated materials that are already in the library of nTopology. In this case, we're going to use a nylon 12 material, which isn't listed already. So I'm going to click isotropic material, and I'm going to choose my linear elastic properties. So we've also got some thermal properties that we can populate, but in this case, we just need the linear elastic properties. Now I know the Young's modulus for the nylon 12 I want to use is 1700 megapascals. Parsons ratio is 0.33. Now we have our model all set up. The model is meshed and we have assigned a material to the model. So now we go into our objectives, what we're trying to achieve from this topology optimization. So we've got a goal to minimize and choose the design response that we want to minimize. So we can minimize displacement, minimize stresses, minimize the volume, natural frequency. In this case, we're going to minimize the structural compliance. So essentially maximize the stiffness of the part. And to do this, we need some load cases. So we're going to need a displacement restraint, areas to hold and fix. I'm going to make this a variable. And we're going to need a couple of forces. I'm also going to make a variable. So for the displacement restraint, we can select the area by a body, so an implicit model, a boundary by flood fill, so we can select certain triangles from the mesh. In this case, we're going to use a face boundary because we've already got some CAD faces that we selected earlier. For the displacement restraint, I'm going to use our interfaces. So at the areas that the two clamps intersect with each other, I'm going to make this our displacement restraint. I'm going to make these faces a variable. All these displacement restraints. Move this up into our variables section up here. The mesh that we want to apply is the FE volume mesh that we've just created, and the entity will be the nodes. So now all I have to do is apply the faces that I want to use into this displacement restraints block up here. In this case, we're going to use the interfaces. So just drag and drop that. And we have created displacement restraints on all of these faces. And again, the reason for using these variables tabs is that we're starting to make a mini workflow. So if I decide I don't want to use those interfaces, I actually want my bolt holes to be our displacements. I just drag and drop them into the block. And now our bolt holes are going to become our displacement restraints. Okay, so I'm going to stick with our interfaces. And we will move on. Let's just rename this. Displacement restraint. We'll move on to setting up our forces. Again, I'm going to use the FE face boundary because we've got some CAD faces set up. This force is going to be our force. I'm going to make our faces a variable and call this vertical force faces. Drag and drop these into our variable section. The mesh, again, it's going to be our volume mesh. So I can either drag and drop this volume mesh into the block here, or I can just double click and it's going to give me all of the possible options that I can have in this box. So I'm going to click our volume mesh. And again, I'm going to go with nodes. In this case, we need to apply a force. So this vector here is going to be the force. In the vertical orientation, the force is going to be in this axis, which is the x-axis, and it's going to be applied upwards. So this is actually in the negative x. Now I know that my scanner is around 1 kilogram, so I'm going to add a 20 Newton force just to give us a little factor of safety there. Now all I need to do is drag and drop my vertical force faces into this chip here, get a visual representation of where our vertical forces are being applied to. I need to do the same for our 90-degree force faces here. So I can either go through the same process again, adding a force here, but we've got most of it set up already. So I'm just going to duplicate this variable. I'm going to call it 90-degree force. And we'll make a new variable, the 90-degree force. The vector is going to be slightly different in this case. This time it's going to be in the z-axis. It's going to be in the positive z. We're going to make this 0, 0, 20. Move this up into our variable section and apply our 90-degree force faces to that tab. And again, we get a visual representation where our 90-degree force faces are acting. So we have our forces and our displacement restraints all set up. Last thing I need to do, so we went through this tab here, we added displacement restraint, added our vertical forces, and then I copied our vertical forces to create the 90-degree forces. Just need to drag and drop the 90-degree forces into the boundary conditions to complete that block. The last thing we need to do is set up our optimization constraints. So we've got quite a few to choose from here. We can add a displacement constraint, so we can set the model to ensure that there's not too much flex, so that certain points don't protrude outside a set displacement. We can add an overhang constraint for additive manufacturing to make sure that all overhanging faces are self-supported. We can add planar symmetry to make sure that the part's completely symmetrical. Stress constraint to make sure that there aren't any areas that go over a certain stress threshold. In this case, I'm going to add a volume fraction constraint. This gives us control over how much material is removed. And I'm also going to add a passive region constraint, because there are some areas of the model that I want to make sure are kept throughout the optimization. So to set this up, I'm going to create a new section called passive region. First region that I want to make sure is kept will be these interfaces. The interfaces between the two parts are quite important to make sure that they're kept in the topology optimization so that the parts fit together again once the optimization is finished. Now at the moment, these are just CAD faces. So the first block I'm going to need to create an implicit body from a CAD body. I'm going to make this, no I'm not, I'm going to use, we've already got the displacement restraint faces set up here. So I want to make sure that when I rerun this workflow, the areas that I apply as my displacement restraints are kept as passive regions. So I can use my displacement restraint up here. And this is just going to turn these CAD faces into surfaces, implicit surfaces, which aren't super useful to us at this point. I'm going to need to thicken them. Apply a thicken body block. Drag my surfaces into here and thicken them by 5 millimeters. So what this is going to do is apply 5 millimeter thickness to those surfaces. It's going to do it at 2.5 millimeters each side of that surface. This has created 72 thickened bodies because each CAD face has created its own separate body and has been thickened. I don't actually want the 72, so I'm going to create a Boolean union, put them all in here, and that's going to create one single body. I'm going to make this a variable, and I'm going to call it strength. There are some other areas in this model that I want to keep as well. I want to make sure we keep our mounting faces. I want to make sure that we keep the bolt holes. So I'm going to duplicate this variable. I'm going to call this our regions. And I'm going to create a separate variable for this called passive regions. Now all we have to do is drag and drop. This is set up as a CAD body at the moment, so I just need to hit this drop down and enable it to accept CAD face list. So if I drag and drop my bolt holes into here, it's going to run through that same little MIDI workflow, going to convert them to an implicit, thicken them to 5 millimeters. Now in this case, I have two passive regions. I want to keep my mounting faces and I want to keep my bolt holes. This block just accepts a list. I can't put two lists into one list. So I just need to add another block called concatenate lists, where I can merge two lists together. I'm going to merge my mounting faces, my bolt holes. I'm going to make this a variable just called lists merge. That into this block. This little mini workflow is going to rerun, create thickened bodies for the mounting faces and the bolt holes. The last thing I want to do in this section, create a Boolean union of the passive regions, those displacement restraint faces, make this a variable and call it final regions. Now if I go back to the passive regions for the topology optimization, we can select regions by CAD body, which like we did for the displacement restraints and the forces up here. In this case, we've created an implicit body, so I'm going to apply it as a region by body. The entity I want it to select is going to be the cells of the mesh, and the body is going to be the final passive regions body that we've just set up here. Okay, so our topology optimization is off and running. Let's make this a variable and just call it topology optimization result. That's fine. It's a fairly computationally heavy task to do a topology optimization, but in nTopology, because it's doing it all through maths and algorithms, we're able to do multiple things at the same time. So while the topology optimization is running, we are going to jump ahead and start creating a lattice on this face here. So the first thing I'll need to do is just select some CAD faces I want to turn into lattice structures. All I'm doing is holding down Control and left clicking to select all of the faces that I want to turn into a lattice. Now, for the purposes of the webinar, I'm not going to go in and click every single face. So you've probably seen me click on enough CAD faces already in the last half an hour or so. I'm just going to select the main few, make sure we get some the kind of really detailed and more intricate faces, just to make sure that we give the software a bit of a challenge when we convert this into a lattice. I think that should be enough. Let's select these last couple in the middle here to make sure that we've got a continuous mesh. That should be okay for now. So I'm going to right click and create a CAD face list. And this is going to, it's not going to be our passive regions. This is going to be our lattice faces. Okay, so to create a lattice, I'm going to firstly need a mesh to lattice. And at the moment, all I've got is CAD faces. So I'm going to have to create a mesh from CAD body. My CAD body is going to be the lattice faces that we've just created. And we have now turned that CAD face into a mesh. We've actually turned it into a series of meshes. We've got 49 meshes here. So I'm going to merge meshes, drag and drop this into here so that now we just have one single mesh. So from here, I'm going to start building my lattice, and I'm going to make a Voronoi surface lattice. Search for surface lattice. Here we are, Voronoi surface lattice. And this is asking me for some seed points, a thickness for the lattice, and a mesh to kind of constrain all the points to. My seed points are going to be random points on a mesh. If we were making a volume mesh, we would need a volumetric mesh or an implicit body. In this case, we're going to do random points on a mesh. We've already got our mesh here. Let's make this a variable quickly. Mesh for lattice. Got a few a few variables that we can change here. We can change the point count, spatial weighting, the relaxation iteration. In this case, I'm going to make the thickness of the lattice 2 millimeters. And again, we're going to use the same mesh to constrain that lattice too. And there you go, really quickly, we have turned that into a lattice. Now it's probably got a bit lower point count. We want these a bit tighter together so that we don't have this odd mesh out here on its own. So let's increase that to 150. Change random seed to try and get that last point joined up. We need a bit more here. I just have some areas missing in this lattice face. Add an extra space to this list. Should. Okay. So something that we have got in this lattice, we've got some sharp corners between all of the beams. We've got sharp points in the intersections. So I'm going to add a smoothen body block mesh to make this lattice nice and smooth. Smoothen iteration, I'm going to change to 1, grid size 5, but we're not losing too much surface, and now we've got a nice smooth lattice structure. And there might be some variables that we want to change in here. So let's make this point count a variable, and let's make the surface, the thickness of the lattice a variable as well. And we'll also change it to a scalar field. We'll see why a bit later. So now I can really quickly change the thickness of this lattice, run it through the smoothing operation. That's the final result. So now we've got a nice smooth lattice to clamp our scanner to. I'm going to make this a variable, rename it final lattice. Drag these couple of variables that we've created into our variables block. One thing we should have done is I should have made this CAD body a variable as well. So let's do that now. Let's make this CAD body a variable. Call this areas surfaces to lattice. Drop our lattice faces this block. So it's just going to run through that process again. Here we go. Here's our lattice is complete. Let's jump back to our topology optimization. Now that's all finished. Here are raw topology optimization results. That's topology optimization study. So you can see that these areas are the areas in the stress paths where it's kept material. And we've got some nice clean faces on these passive regions that we've told the topology optimization to keep. Now from here, we could maybe decrease our threshold if we wanted to add a bit more material. Go the other way if we want to make it a bit lighter. In this case, I think 0.5 is, yeah, result, and we can pan through our iterations to see exactly how the optimization was built up from the passive regions at the start, adding material right through to our final result. So now I'm going to need to turn this topology optimization result into an implicit body so that we can rebuild our final part. We go implicit body from CAD body, drop the optimization results in. Now we've got some quite rough areas in the middle here from the raw results. So I am going to again use our smoothen body block, topology optimization. I'm going to take that smooth iteration down a little. We just increase this grid size, give us a nice smooth surface. You can see the smoothen body block has taken away some of these surfaces that we wanted to keep. But because we've made them implicit bodies, we're going to merge that back in when we go to create final model. So let's call this smooth topology optimization. Now let's start assembling all the pieces of the puzzle. So we're going to do a Boolean union operation where we're going to combine our smoothen body with our final lattice, which is going to look something like this. But we're also going to include our final passive regions as well. So quite a complex task to combine all of these into a Boolean union, but in nTopology, that all happens pretty quickly. Something that we might not like in this union is that between all of the bodies, between all of the separate bodies, we've got sharp corners and sharp edges in between all of these intersections. Now in a traditional CAD package, to try and put fillets and radiuses in all of those intersections, it's going to be a really difficult task. But in nTopology, all we need to do is select the blend radius that we want between all of these bodies, let's say 4 millimeters, and in just a few seconds, that's going to return us a result that unions all of those bodies together with a 4 millimeter blend radius between all of them. So a really, really complex task that a traditional CAD package would most likely fall over and crash with. But in nTopology, it happens in just a few seconds. So the final thing we need to do here is this Boolean union that we've made overhangs our design space in quite a few areas. So I'm just going to do a Boolean intersect. I'm going to intersect this body that we've just created with our body to mesh, which is the original implicit body that we started the process with. Now we've got our final part with some nice sharp edges on our mounting faces, our interfaces, bolt holes. They're exactly as we wanted them. We've got a nice lattice structure around, merged with our topology optimized part. So let's make this a variable, call it final part. Okay, so now we can change some of these variables if we want to. Maybe at this point we decide the lattice, we want a few less point counts. Maybe we want the thickness to be a bit less as well. Topology is going to go away, rebuild that, give us a new model with a lower point count for the lattice and a much thinner beam thickness. It's going to go away and run that now. Now we can start to convert this whole workflow and we can condense it into what we would call a custom block. Our new result with bigger spacing for our lattice. Probably in this case that is a bit too thin, so let's change our we'll change our thickness back to 3. So let's convert this whole workflow into a really easy and simple to use custom block. First thing I'm going to do is our output for the custom block should be our final part. Let's drag and drop that, the output. And then all of our variables, I'm going to remove all of these links to the faces. And I'm going to drag and drop all of these variables into our input section. We should have everything we need here to create a custom block and be able to really quickly reuse this workflow over and over again. So we should have a body to mesh, some restraint faces, vertical force, a 90-degree force, passive areas. To just remove that link, put our passive areas into our inputs. Faces to lattice, point count, and the thickness. Perfect. Now I'm going to save this as a CB for custom block. Lightweight and okay, let's save that. And then I'm just going to flip to a new instance of nTop. So here, this is pretty much where we started the last one. We've got our left-hand side clamps, our right-hand side clamp, and we've already done those first few steps. We've converted it to an implicit body and just selected out some of our CAD faces that we want to use. So I'm going to go File, Import, bring in that custom block that we've just created. Just going to take a second to load up. Remove some of these pre-populated lists. I'm going to duplicate it because we're going to use it twice. Actually going to duplicate it again because I'm going to use it a third time a bit later on. So all of that workflow that we just created is now packaged into this super easy custom block. And all of the work, the kind of half an hour that we took to build that workflow, we can now do the same operation in literally a minute. So it's going to ask us for a body to mesh, edge length and growth rate are fine. Displacement faces, going to be our interfaces, vertical load faces, 90-degree force faces, point count and the thickness for the lattice, the surface to lattice, and the passive regions, which in this case will be our we need our mounting faces and our bolt holes. So I'm just going to do that same lists, mounting faces, bolt holes, drop that in there. And that's all we need to do to set up that first block. Now let's redo the same for our right-hand side block. The body to mesh, displacement restraints are going to be our interfaces, vertical force, 90-degree force, surface to lattice, passive regions. In this case, we don't have any bolt holes to worry about. All we have is our mounting faces that we want to keep. And in this case, I'm going to change our thickness to this ramp block that I created earlier. So the thickness for the lattice, rather than just being 3 millimeters, I'm going to get that to change using this ramp block. So I've set up an implicit body, which is just a sphere in the middle of the part. And in this ramp block, I'm saying at 0 millimeters from the sphere, I want my lattice to be 5 millimeters thick. And at 40 millimeters away from the sphere, I want my lattice to be 2 millimeters thick. So let's visualize that quickly on here. And a contour interval, just pan back a little bit to give us a bit of context to what we're looking at. So this is the field for this ramp block. I'm saying anywhere 0 millimeters from the sphere, I want my beam thickness to be 5 millimeters. And as we get further away, it's going to change to 4 millimeters, 3 millimeters, 2 millimeters. Anything outside 40 millimeters away from that point, the beam thickness is going to be 2 millimeters. So these custom blocks working away in the background to create those two implicit bodies. It's going to create so it's going to mesh this body. It's going to complete a topology optimization based on these restraint faces and these force faces. It's going to add a lattice with a point count of 150 to the surface that we add in here. It's going to keep these passive regions, and it's going to apply this thickness to the lattice once it's created. Now, just to show you how robust this this block is and the workflows are in nTopology, I'm going to do another custom block to a completely different geometry. I'm going to choose this bracket here. Just going to import this in as a step file. It's going to be a completely different geometry to the ones that we've been looking at previously. Might just take a few seconds because it's loading some other parts. So the block is asking me for a body to mesh. Let's convert this to an implicit body. Drop that in here. It's going to ask me for a displacement restraint. Let's say that these two faces maybe are the displacement restraints. It's asking me for a vertical force. Let's apply the force to this area here. Asking for a 90-degree force, which I'll apply to this surface. Surface to lattice, maybe we want these faces to have a nice lattice on for whatever reason. And it's asking me for some passive region. So let's say we want this surface to be its passive region. So it's a completely different model to the clamps that we have been looking at, but it's going to work through exactly the same workflow, create a mesh from this implicit body that we added in at the top. It's going to mesh it to this edge length with this growth rate, and it's going to use the displacement faces that we set up, the vertical force, the 90-degree force faces. This is the point count and the thickness for the mesh, surfaces to lattice, and we have also applied a passive region. So we've got these three custom blocks all running in the background. Typically take a couple of minutes to process and to finalize. So let's just turn on the visibility for them all, and they will pop up once they've finished. This one is nearly finished, so that's the first half of the clamp that we were looking at. You can see kind of the power of the custom block and the workflow tasks that went into building the first one is done. And now we can just reuse this workflow and let it build it itself. You can see the results of the ramp block that we used here. So a much thicker beam thickness for the lattice in the middle where that sphere was, and a much thinner beam thickness as we get further away from that sphere. There we go. There are 2 topology optimized clamps, and just as a reminder where we started, our original CAD bodies that we brought in. So you can see a massive reduction in the volume of material that we've used. And that's what's created such a huge weight saving and cost saving for these parts. And the final custom block that we did is created some slightly strange results, but we did give it some quite strange operations to follow. But just to show you how robust that custom block is, even though we've picked a completely different geometry, we've still been able to come up with a result, topology optimized result, with a lattice on the surface. Cool. Okay, so we're pretty much nearly out of time anyway for the webinar. Keen not to keep you all any longer than you potentially want to stay on. I am happy to answer any questions that anyone might have, so please feel free to drop a question in the Q&A or just stick your hand up and I can answer any questions for you. So yeah, if you've got any questions, then please just shout and let me know. If not, then we will conclude the webinar here. I'll just hold on for a couple of minutes to see if anyone does have any questions. Okay, no one forthcoming so far. If you do have any questions you want to ask after, please feel free to get in touch with me through LinkedIn or through my email address, which you'll probably find on the registration for the webinar. So great. Thanks all for listening, and please give me a shout if you've got any questions. Cheers.